I'm Dr. Hay. I'd like to tell you about when Gauss's law is useful. This is Gauss's law. On the left side we've got the flux, and on the right side we've got the charge enclosed inside of a Gaussian surface over epsilon naught, a constant. Now, Gauss's law is used to find the electric field E, but here's the problem. E is inside this surface integral. I've put the S here to indicate that it's a surface integral. And this is dA, the area. So when E is inside the integral, Gauss's law for our cases only really becomes useful when you can take E out of the integral and you can get rid of the dot product. So here's the two conditions that you want to be true in order to use Gauss's law. Gauss's law, and I should say, is true for any surface, but it's only useful if you have these two conditions, and here they are. 1. If E and dA are in the same direction. In other words, if they're parallel. If the vector E, the one that you know you're going to find, so you have to have some idea of the shape of the electric field, and the surface area, the differential area, something pointing away from the Gaussian surface, if these two are parallel, you know that when you take a dot product between two parallel vectors, you just get the magnitude of those two vectors multiplied together, and the dot product basically goes away. It's the cosine of 0, so you just get E times dA. Now there's another thing that needs to happen in order to isolate E, and that's to take the integral. And so the other condition for Gauss's law to be useful is for E to be constant over the surface, the Gaussian surface. Not necessarily the surface of your object, the Gaussian surface that you've chosen to draw. This is this invisible surface that you draw around an object when you're trying to find the electric field. So constant over the surface, in other words, over dA. If these two things are true, then this side of the equation has changed to become this. The dot product goes away because E and dA are parallel, and E is constant over the differential. In other words, it can come outside the integral. So you've just changed the left side of this equation to the magnitude of E, I'm going to draw it with the bars around it, times dA, and that's still the surface integral of dA. So the integral has moved inside, and now you've got two things isolated. And let's go ahead and write the other side of the equation here. Q enclosed over epsilon naught. So now you have the electric field isolated, and this is the surface area of the Gaussian surface. And this is the charge enclosed inside the Gaussian surface, and here's the constant. So once we can find the area of the Gaussian surface, then you can divide this onto the other side, and now you've got the electric field, the magnitude of the electric field.